So, okay, so what's the problem we're trying to solve here? So in general, we're interested in being able to integrate data or use data from a number of different sources. And traditionally, there's a couple different approaches to that. One is sort of the traditional data warehousing approach, where all the information is sort of loaded from a number of different sources and put into one place and then queried. And then there's sort of the virtual integration approach, where the idea is you don't actually move the data, but you want to provide some kind of integrated access to a bunch of data and do it virtually. Now, in either one of these approaches, you need some way of actually describing describing the contents of the different sources in order to be able to integrate them. And traditionally, that's done using what's called a domain model, where you basically have a description of what's in each of the sources. It describes what the people, events, and all their attributes are in the various sources. And this is used to essentially, in this one, which is to essentially create a set of what are called source mappings. So the idea is that you're going to describe the contents of each of these sources and how it relates to this domain model, right? And so then the question becomes, well, how do you actually get these source mappings? And the traditional approach in many data integration systems is to manually encode these things, but that's a very hard problem. And so we've really tried to make this process much easier, and that's really the focus of what I'm going to talk about today, which is how do we actually create these kinds of source mappings that describe different sources, that allows you to pull information from different sources that may be in very different formats, very different, even different types of forms in databases, Excel spreadsheets, or CSV files, or XML, and then be able to query them. So here's the basic problem then that we're looking at here, which is this what we call automatic source modeling, right? So I'm given some domain model, which is about the domain that I'm interested in, a set of samples of the source data, right? So I have a particular source, and then somehow I want to basically build this semantic model of the data. And once I build that model, then I output that as a set of source mappings, right? One mapping per source. Okay, so we've developed this tool called Karma, which attempts to help users automate this process, right? And so it essentially follows the same idea, where I can take in a variety of different kinds of sources. So across the top here, I've got relational sources, hierarchical sources, or even online services. I've got some kind of domain model for whatever domain I'm interested in working on. And Karma is the tool that basically takes all this as input, and then interactively, with a user sort of driving the process, builds these source mappings, right? That essentially go from the source itself. It builds this description of the source in terms of this domain ontology. Okay, so and then the output. Well, the output can both be the source mapping itself, but it can also be used to actually generate the data in a standard format. So, for example, Karma can output the data in JSON-LD, which is just a linked data version of JSON, which is an internal Java representation people often use. Or you can output data in RDF, which comes from the semantic web world, which is a very simple sort of representation. You can essentially take all the different sources you have and convert them into either one of these sources, either virtually, meaning you do it on the fly, or you could do it in advance and create an integrated data source. Okay, so let me now talk about what it means to build a semantic model. What does a semantic model actually mean in this case? And so what I'm going to do is take a very simple source here. So I have a source that contains just 2 rows of data. I know that's not your typical data source, but that's what fits nicely on the slide. So we're going to use it to describe this. But imagine it's a database with 1 million rows, and I want to build a description of what this source contains. And then below the source here, I have the domain ontology. Now this this domain ontology is about people, organizations, events, and places. And you can see that for each of the classes of information, those are shown in these sort of red oblong circles. The links between the different classes are shown in black. So maybe a person, one thing that could be represented in this domain ontology is this person is born in a particular place, right? So person born in place, person lives in place. Then I can also have different properties of a person, right? So I can have a person's birth date and a name. And so you can see for each one of these classes, I've got a set of properties and then links to other classes. Over here, I also have this notion of subclasses, right? So I can have places, and then city and state are both a subclass of place. And there's a relationship between city and state, which is city is in some state. So this is just a very, very simple domain model, or rather domain ontology, and then a very simple source. And I can use that to sort of show what it means to build a semantic model of the source. So, okay, on to the next slide. So these are what are called the semantic labels or semantic types. So you can see that each column of information represents some piece of information, right? It consists of both a class and the property of that class. So for the first column, for example, represents the name of a person. Then we have the birth date of a person, the name of a city, the name of a state, and then the name of an organization, right? So those might be the the semantic labels that we want to put on. And notice each one of these comes from the domain ontology, right? So the labels actually have to map directly to the domain ontology. If the domain ontology doesn't cover all the data, then you either have to extend it or you would ignore that particular piece of information. But that's only part of it, right? So you have the labels. Now we have the source model. And so this represents the relationships between these different columns. And notice that in this model, before with the previous one, I had a person and a name and a person and a date. They weren't necessarily connected. But once I build the model, I say, well, there's a single person here, right? It has both a name and a birth date. And it's the name and the birth date for this person. In this case, the model is that, okay, this person works for this organization, right? Was born in this city. This city is located in this state. And that's the whole model for this particular source. So these are the kinds of things that ultimately we want to be able to create to support this problem of being able to integrate data across different sources, query information across lots of sources. It basically repurpose or understand the information that's in each of these sources. Okay, so here's our basic approach to actually being able to do this. So we're going to start out with a sample of data, like I just showed you, the domain ontology, and then we go through essentially 3 steps, which I'm going to describe next. The first one is essentially learning the semantic types. So, is there a way we can actually figure out what these semantic types are very quickly using some machine learning techniques? Then the next part is actually coming up with the model, right? This semantic model of the data sources. And that's a 2-step process shown in this diagram, which is first we're going to construct a graph of the data source using the domain ontology. And then we're going to extract the relationships from this graph using some graph algorithm techniques. So let me go through these. Okay, so first let me start with learning semantic labels, and you'll see I have some references to papers as we go, and I have some links at the end of the talk so you can get more information. Okay, so the basic problem then of learning the semantic labels is as I just described, right? I want to be able to take that data source and come up with the labels shown right above it. And there's a couple of requirements in terms of what we're trying to do here, because we're basically want to develop these techniques and embed them in this system that I mentioned, Karma, that allows users to do this process very quickly and efficiently. And because we want to essentially build an interactive tool, we have a couple of requirements in terms of the technique that we need to develop here. One is that it needs to learn from a very small number of examples. I don't want to have to give it lots and lots of training examples in order for it to basically learn these things, because users don't want to label lots of data, right? You may have just a few sources you want to map, and so you want to do it based on a few examples. Second thing is I want to basically be able to clearly distinguish both string and numeric values. String values tend to be much easier than numeric ones, and so we want to be able to support both. And then it also needs to be able to learn quickly, because users are impatient, and so they want to be able to quickly learn something and then apply it to their next source. And it needs to be highly scalable to large numbers of semantic types or semantic labels, because that's what happens in practice. We've seen sources that could have 1,000 semantic types, and so it needs to be highly scalable. So here's the basic problem then, or the basic idea of what we're going to do here, which is, here's an example source on the left. This is a source about soccer players, and you've got a name, position, and height. And another source here, we have a very simple source that seems to just have height information, right? And we don't know what these semantic labels are for this second source. And so then the challenge is, okay, how do we figure out what the semantic labels are for this new source, comparing it to the original source? And you can note here that, okay, if you look at sort of the content and information here, it's very different than this, right? If you compare the birth name to this source up here, they're quite different. But if we look at this information here, in the third column, this height information here seems very similar to the height information over here. And in fact, you can see the label here it doesn't say height because it's in a different language, but you can still see that the values are very similar. So the general idea is to essentially take each new source and compare it to the known sources and look and see if you can find the ones that sort of have the closest match, and then propose those as the ones that are most likely the semantic type. We do this by comparing a whole set of features. So here's the set of different kinds of similarity features that we can use to do this kind of mapping. The first one is to take a look at the attribute names. Turns out that there's typically a lot of information encoded just in how someone calls the actual name of the attributes. And we use a technique here called Jacquard. Jacquard essentially looks at all of the tokens and compares the tokens and finds how much the tokens overlap. So if you had, person name, that's 2 tokens, and if the other source has name, then it's like, oh, well, then 50% of the tokens overlap. Value similarity, this is now where we actually don't just look at the names of the attributes, but now we can also compare the content. So in this case, we use both TF-IDF and Jacquard. TF-IDF is simply a method for looking at the term frequencies of the terms that are actually being used in the column of information, and looking to see how much overlap there is, right? And TF-IDF takes into account how frequency those terms occur in general, right? So the IDF part's the inverse document frequency. And then Jacquard I already mentioned, but we'll see. We have a little refinement of Jacquard so that it works better for numeric values when you have numeric. And then over here we have distribution similarity. So we can also use, when it gets to numeric data, we found that it's very useful to use statistical tests. And so we can use both the Mann-Whitney test and the KS test. These are both statistical tests that sort of say how similar some set of attributes are. And then finally, we have the histogram similarity, where again we can use the Mann-Whitney technique to compare histograms. Okay. All right, so let me just show you in a little more detail how some of these similarity measures work. So if we have this first one, which is the name similarity, which is looking at the attribute names, we can see here that first name and where it's 2 words, lowercase, is very similar to first name, all is 1 word, right? So and it's not at all similar to address. And so you can see that we can use this kind of information in a lot of cases to help figure out which things are similar. Value similarity is a little more complicated. So I mentioned we can use TF-IDF or Jacquard. So here in this case, we're looking at the contents, and notice that there may be some overlap, like Cahill and Cahill, or 1 and 1. But even in cases you don't have overlap, you also can find similarities just because things are very close, right? And so a lot of the techniques we use, like TF-IDF, will do things like stemming, which removes, different forms of the words and those kinds of things. And you can see that, these names are not at all similar to the names of these different football clubs. Okay, so that's value similarity. And then when it comes to numeric value similarity, what we found is, well, just looking at overlap into the numeric values doesn't work very well. So we developed sort of a refinement on that, which we call numeric Jacquard similarity, which simply looks at the range of each of these, right? And so that's best explained here, right, on this graph, which is that if I have set 1, which covers values between 0 and 60, shown in yellow, and set 2 that covers values between 20 and 100, then the overlap in these is between 20 and 60, right? And so the entire range is 0 to 100, and so you can see how much these 2 things overlap, and you can decide how similar they are based on the degree of overlap in the ranges. We also have, I mentioned distribution similarity, right? So this is looking at things like how frequently certain kinds of distributions happen in the data. And so if you're trying to compare one data column that has information about the number of games played in a soccer context versus the number of goals scored, then they're going to have a very different kind of similarity, because it turns out soccer, people don't score many goals, and so you're going to have this sort of distribution like this, whereas the number of games played might be much more flat like this. Okay, so now I've described the sort of similarity measures we use. Then the question becomes, how do we actually train a model to actually do this, right? And so the key idea here is that we have all of these different similarity measures, okay? And what we're going to do now is take 2 sources. I'm going to do this by example now. So in source 1, I've got a player and he's got a name and a height. In source 2, I just got a player and he has a name, right? And what I'm trying to do is actually train the system. So I actually know what the semantic labels are for both of these 2 sources, right? And what I'm doing is I'm training the system and building a machine learning classifier so that when I see other sources I haven't seen before, I know how to classify them either as a match or not match. Okay, so really what this is telling me is that, okay, this source 2 here is the same as this first column in source 1. Right, and we can see, the way this works is we're going to compare the first column of source 1 to the first column of source 2, And I'm going to compute these similarity scores. So for each one of those similarity metrics I just described, we're going to get a score for how similar those are. And that's labeled as true, and that gets fed into the machine learning classifier. Likewise, I'm going to actually look at the relationship of the second column in source 1, height, and compare it to this source 2 here. And I'm going to record the set of similarity measures for that. So the Jaccard score for that is 0.05, and the cosine is 0.1. Now notice, I haven't listed all of the different similarity measures here just because there's not enough space in the slide. But in fact, you would compute the scores for every one of the similarity measures. And note that the second one is not a match. And so this is labeled as false in front of the classifier. So in a machine learning classifier, you're going to label both the true and the false examples. And then that gets fed in. And then what the system does is it learns a classifier that sort of says, oh, okay, if I see a combination, it might, for example, learn something that says, well, if I have a Jaccard measure of at least 5.5 and a cosine measure of at least 7, then that's going to be likely to be a true positive. And so it's going to do this for a whole bunch of examples, train up the classifier so that it can actually recognize these things. And then in the next step is I'm going to basically take a new source I haven't seen before, and I'm going to say, okay, tell me the semantic labels for this new source. And the way it works is I'm going to basically compute the similarity measures between each of these known semantic types, so player and height. I'm going to compute scores for each one of these. And then for whether or not this matches this first column, first column of the first source, which is the name, it's going to give me a score for that and say, oh, okay, I believe that's true with a total score of 0.8. And then whether or not it matches the second one, it gives me a score of 0.1. So clearly this first one is much more likely to be a birth name and not a height. And note that this is embedded in Karma, and so the user ultimately gets to decide. So what it's going to do is it's going to present to the user what it thinks are the most likely matches ordered by these scores. And then ultimately the user can override them if the system somehow gets it wrong. But this works quite well, and it's quite scalable. So that's the first step. Let me now move on to the second piece, which is actually building these semantic models in Karma. And this is the second piece I already described, which is creating the basic, not just the semantic labels for this source, but also the relationships between all the columns. So okay, so the first step, and in my overview I showed before, is to essentially construct a graph of this data. So I'm going to go from this information and build the graph using this domain ontology. And what's happening here is I'm going to look at what are the possible relationships between each of these columns using this domain ontology. And when I do that, I'm going to get a graph like this, right? And so each of these yellow nodes correspond to the semantic labels that are already identified. And the links between them are the links that come out of the domain ontology. And the weights on these graphs essentially are used to essentially in the next step. But essentially the weights are sort of the likelihood that each one of these is a link between let's say person and organization or organization and city. Okay, and so what happens after we construct this graph is we're going to have to actually decide what the most likely relationship is. And we do that by essentially searching for a minimal explanation. So the graphs have weights, and so now all I have to do is extract from this graph sort of the minimum weight graph that describes the links between all of these columns. There's an assumption here that all of the columns are actually linked together, but that's typically true. They're not usually in the same table if they're not related. And we use what's called a Steiner tree, which is a particular type of algorithm for essentially connecting these semantic types over this ontology graph. And you essentially find this graph that spans the entire set of nodes, those yellow nodes, with the total minimum cost. Now the problem here, of course, is that this problem is NP complete. It means it's computationally quite hard, but there's some very nice approximation algorithms that we use here. So there's one by Ku et al, where the worst case time complexity is order v squared s, which v is the number of nodes, s is the number of the Steiner nodes, which are the labels, the semantic labels in this case. And that gives you an approximation ratio of no worse than 2. So it's no worse than 2 from optimal. Typically, it's much better than that. Okay, just to give you a sense, so what actually happens in a Steiner tree algorithm? I'll just go over this very quickly, but it just gives you the intuition about what actually this search process looks like. So we start here with the initial graph that I just showed you, right? And so the Steiner nodes are the ones shown in green. And this is just a made-up example. It doesn't correspond to the example we're looking at. And you can see that there's weights on the links between each one of these nodes. And our challenge is to actually come up with the minimum tree that represents this, which will then correspond to our description, right? From this minimal tree, we can then get the semantic model of the data. And so the first step is we're going to construct the complete graph, meaning we're going to come up with the minimum cost path between each one of those Steiner nodes, right? The nodes are the green nodes, those correspond to the semantic labels. And so that would, for this initial graph, you see this comes up with here where all the links have a weight of 4. And you can sort of see here, if you follow these links, right, I go from V3 to V4. I don't want to take this one because it has a weight of 9, but I can take this one, it's 2 and 2, and that gives me 4, right? And so this is the complete graph with a minimum cost link between them. Then I compute the minimum spanning tree. So that's the minimum graph that actually covers all the nodes and drops in the extra ones. There's a linear time algorithm for doing that. So we can actually build a graph that looks like this, where we drop these extra ones, because I can now get between every node to every other node. Then I'm going to take each of those links and replace them with the corresponding shortest path in the original graph, right? So if I look at V2 to V3, the shortest path from V2 to V3 is probably going from V2 to V6 to V5 to V3. It's not V2 to V3 directly here because that has a cost of 8, and this other path here has a cost of 4. So then I build this path. Then I again compute the minimum spanning tree, which is a very efficient algorithm, and that's going to drop off some extra links that I don't need. And then finally, I remove all of the extra links that until all the leaves are Steiner nodes. So I don't need to keep these because there's no Steiner node here. And then I have this tree. And from this graph, I can now extract the relationships between the sources, and that's going to be my proposed model. So that would produce something like this. So I've inferred this relationship. I've constructed this minimum tree that connects all the semantic types. And so I have this initial model. Now, this may not actually be the correct model. And one of the things that Karma allows you to do is allows the user to go in and refine this. And it's important to note, if you look at that original table I showed you, right, in some sense, it's hard to understand what the semantics are unless you're already familiar with the data, right? You need some background information about that source to really understand what the relationships are. So the initial thing that Karma comes up with might actually be close but not correct. So this would be the model that Karma would actually show you. So it would produce this model for you, and then this says that okay, the organization has a CEO who's a person, but it turns out that the actual relationship we're looking for in that table was this one, where the person was born in a particular city and worked for that particular organization. And so the user can just click on these nodes in Karma, sort of correct those 2 links, and then Karma would then have the correct model here, which is that, okay, the person worked for this organization and the person was born in this city and has this other information about it, right? So this is the name of the person, the birth date, and so on. So okay, that's the first piece of the talk, which was to tell you about how this actually is done in Karma. And now I'm going to spend a few minutes and tell you about some more recent work we've been doing, where that approach in Karma essentially is very interactive. It's nice. It's a nice tool. I'll give you a link to it at the end that people actually are using, and we continue to support that tool. It allows you to very quickly and easily build these semantic descriptions of your sources, so then you can use those models to integrate data or query them. But it still takes some effort on the user's part. And so we've been looking more recently at other ways we could sort of minimize the amount of user effort required to actually build one of these semantic models of a given source. And what we've been doing now is looking at using what are called knowledge graphs, existing knowledge graphs, to basically build these models. And so here's another example table, not all that different than the last one, but this one's about political parties in Austria. And what we're doing here now is sort of saying, well, let's take a source like Wikidata. If you're not familiar with Wikidata is a really nice, very useful source. It's a lot like Wikipedia, except that it has data for, it has structured data instead of sort of textual information about it. A lot of information in Wikipedia is actually also linked to Wikidata, but Wikidata is really extremely large. It's got billions of pieces of information, billions of facts in it. and it continues to grow in sort of use and popularity every day. So our idea then is to sort of say, well, why don't we see if we can actually use Wikidata to help us build these descriptions of a source? Because if we have a table of information and some of that information is actually contained in Wikidata, then we can exploit that fact to actually figure out what the description of the data is. So let's say that you're given this table here, which is the third presidents of the National Council in Austria. Third presidents are like, well, in the US, we have vice presidents, which would be second presidents in Austria. Third presidents would be the ones that came after the vice president. And so here's a simple table. And then here's the model of this table, or the description of how that table would have been modeled in Wikidata. So Wikidata has its own sort of modeling technique where you have what are called statements. You also have these classes like humans and political parties, and you can have a property like third president. So what we're trying to do here is actually figure out, okay, how would we describe this data source in Wikidata? Then we'd have these statements about this, and notice these things like this P39. These are every property in Wikidata has both a name and a number. So P39 is position held. It makes for a very concise way of describing things, right? And the start time, so the time that this person entered office would be the start time, which is P580. The end time is P582. And then the particular position held would be third president, right? So that's P39. So our goal then is to be able to basically take a table and to map it into the Wikidata ontology using this kind of format where you have what are called statement qualifiers and statement properties and statement values. It's very similar to the model I just described, but just they use a little bit different terminology. Okay, so all right, so here's the main idea then. So I start out with this table, right? I have a table, let's say from Wikipedia. It's got these, it has these third presidents listed with their start and end times and what party they were in. And then over in Wikidata, I have a lot of information about some of these individuals, right? And it turns out in the initial version of this work, we're going to exploit the fact that not only do I have this link, but in fact, the link between Wikipedia and Wikidata is actually sometimes explicit, right? So there's actually a link here from Eva, I won't attempt to pronounce her last name, directly into Wikidata. And so if I clicked on this link, it would actually take me to this information over here, which says that, oh, okay, Eva is a member of this political party, has a particular start time, which is, entered office in 2006, left office in 2008. And this is really important because essentially, since I know some information about her, I can essentially use this to help infer what the possible model of this data is, because I already know what the model is in Wikidata. And so you can see here, the start times correspond to the start and end times over there. So very conveniently, this tells me a lot about what this table is, right? That, okay, this is probably not just entered office, but a start time, this is an end time, and so on. And then, oh, the party here, right? You can see that there's a match. We have to do some fuzzy matching here because you can see here that, Grun is over here and P. Grun is over there. So here's the overall approach. So I have a table I want to map. So we'll start out with Wikipedia tables, and I'll describe how we can generalize that later. And then we also start out with Wikidata, right? So we have this entire knowledge graph that we're using for this. And I have a set of contextual values. These are essentially additional information on the page, like, well, what's the the top level category of the title on the page, and there's other information you can sort of exploit from the page. And this correspond to things like the third president, because that's sort of in the title of the page. So that sort of gives us contextual information. And then I go through two steps, much like the previous technique I talked about, which is the first step is to actually build this candidate graph. Which essentially is all the possible links, and I'll go through an example of that. And then I'll come up with my final semantic description, right? How do I decide, well, what's the most likely description of this data given all of the information in this candidate graph? So let me talk about how that works. So, okay, so I'll do this by example so you can get a sense of the intuition of how this works. So here I have a table, the same table I showed you before. And then what I'm going to do is I'm going to take this table and map it to a graph of cells along with the context, right? So each node here, I've got each of these cells here in this table, they correspond here. And I've just shortened these names, but this would be the full name, right? And then I've got the years here, I've got that they entered, the years that they've left, and then the party. And then the contextual information, right? So it turns out other information on the page would give me the context that these are the third presidents. Okay, so what do I do now? So now I'm going to essentially add the links that are actually discovered from the knowledge in Wikidata. So and these links are going to give me are going to go from this table. So let's take this one example, right? So I look up, I have a link in the original table to this Thomas Prinzhorn, and I get to this page here where it says, oh, he's a member of this political party, had this position. Now in this case, he held this position of second president. And this is just to show you an example that everything doesn't always match nicely. Probably there's somewhere else later on this page that also he held the position of third president, because people could hold more than one position. But I'll show you how we take this data and what we do with it. So we essentially see here that his political party's FPO. So this gives me a hint that, oh, okay, this is likely to correspond to the member of political party, or P102. So I can essentially build that link from Thomas to FPO as a P102 link, right? Member of political party. I can do a fuzzy match on this date and sort of say, oh, this seems to match the end time. So I'll hypothesize that this is a P82 link, 582 link, which is the end time, right? You can see down here, P582. That we get to that link as Thomas Prinzhorn goes position held, which is P39, and the particular position held is second president, because that comes from here. And so I essentially have this initial sort of links in my graph from this. Okay. And this is these Wikidata statements, this little green nodes, and this is an entity in Wikidata with the second president. Okay. Now, okay, what about the rest of the graph? So we can follow the rest of the graph in exactly the same way. I'm not going to go through the details of it because I don't have time, but we're going to build all the other links here, right? So you can see we also have P102 links, which are the link to the political party, 580 and 582 links. But notice that the 582 links here correspond to the end times, whereas over here, this corresponded to the begin time. I mean, it hypothesized that because he probably left office as second president in 2002 and then took office as a third president in 2002. Okay, so what's next? So now what we're going to do is we're going to group the links of cells from the same source and target together. So how does that work? So what we do is we're going to essentially say, all right, we're going to take all the P102 links, right? So we have this P102 link here, and we have the P102 links down here. So all of those get linked together. Those are the party links, right? And so we have one link here from P102 to party, and there's a lot of consensus on that. Likewise, we can do the same thing for these P39 links to get to third president. And so we can group those together over here. Likewise, we have P39 links here to the second president. Those are really in conflict with each other, right? Because either this column corresponds to second president or third president, and that we'll disambiguate that in a later step. But those are both candidate descriptions of what's actually happening in terms of the position held. Likewise, we can take a look at these entered office and left office, and those as well as the ones on top, and we can see that if we essentially can then produce the final candidate graph, which looks like this, which is that, okay, I've got a name, and possibly the position held as second president, or possibly as third president, that he entered office or possibly left office in this column here that corresponds to entered office, and that he probably left office in the one that corresponds to left office. Okay, so so that gives us a set of candidate relationships from this graph, right? So these are all the possible relationships. We don't yet know which ones are the right relationships, right? So they're just the candidate ones, right? And then it also gives us a set of candidate column types, right? So this node here is likely to be a Q5, which is a human. And this party node here is either a political party or organization. And part of what we have to do now is disambiguate this, right? And the way we're going to disambiguate this is essentially to select, well, we're going to select the most appropriate relationships and types. The way we do this is essentially going to give us this final semantic description. So, and how do we actually come up with that? So here we have sort of a collective reasoning problem, and we're going to use what's called probabilistic soft logic, which is essentially what's a probabilistic graphical model framework that uses first order logic. And really what happens here is we're going to have a set of predicates and rules, and it's soft logic because these predicates have sort of soft values, right, between 0 and 1. And essentially, you take all the rules, you're going to convert them into some exponential function that then you can approximate and come up with sort of what's the most likely description. So here's just to give you a sense, here's the set of relations that we use in PSL, which is whether or not something is a correct relation, right? And so we'd say that, okay, the correct relation name statement P39. So what we're trying to do is sort of represent in PSL, we're trying to infer which of these final set of relations and final types are the correct ones, right? And so we represent it like this, where we have these different sort of assertions that, okay, these are the possible correct relations. This is just the representation, right? And then we have these set of types, right, where you say, okay, the correct type might be this one, or it might be this one, or it might be this one, right? And so you can see over on the right here, we have to decide which one of these are the correct relations and types. So that's just the set of predicates that we use in PSL. Then we have this set of rules. And so by default, you basically are going to assert initially that all these correct relationships, correct types are false. And then we have a set of rules to infer which ones we think are most likely to be true. And what we do is we use sort of the frequency of the match, right? So the number of times that we see a particular relationship N1 to N2, we take the most frequent one of those, right? So we saw in that case that third president was more frequent than second president, right? Because we had 2 examples of it being a third president, only 1 example of being a second president. So we actually think the correct relationship there would end up being third president. We can also find out when there's sort of contradictions, then those are less likely to be correct relations. And then when you have the frequency of the type matches, then those are also being used to determine which ones are sort of the correct types, right? If you see that type a lot, then you're going to infer this correct type. So for example, we saw the political party was in complete agreement, so it would likely infer the political party. Okay, so given all that, we run PSL against this table, and we end up with this model that I showed you at the beginning, which is essentially that, okay, this is a human, he's got a name, he holds this position, which is third president. The start time and end time are these 2 columns here, and this is the political party. And this is all done without any user input. The key here is that we're able to exploit all this background knowledge to essentially get the system to infer this. And that's the approach. So let me just wrap up, and then we'll have a few minutes for questions. So first, I have 2 contributions I described today. First, I talked about Karma, which is this interactive tool for building semantic descriptions of these structured sources. It has a couple innovations in it that I think are important. One is this scalable approach to learning these semantic labels. And the other one is a semi-automatic approach to inferring these semantic models using this domain ontology. The second piece is this system called Grams, which is a novel approach to essentially building these descriptions of Wikipedia tables, right? So we started with tables that were in Wikipedia that were already linked to Wikidata, and I'll describe future work in a minute of the next step there. But the key idea there is that this candidate graph makes it very easy to represent, discover these n-area relationships, do that fully automatically. And using PSL, we can do this collective inference to come up with sort of the final semantic descriptions. So here I have sort of the next step in that second piece of work, which is, well, what happens? The tables we had were already linked to Wikidata, but what happens if we have a table that's not linked, right? So this is a table that has no links. And we're working on a technique now where essentially we use some entity linking or entity resolution techniques where we take each of these entities that are mentioned in the original source, automatically link them into Wikidata, and then we can apply the same technique here, Graham's technique, to learn this table. And that's work in progress. We'll hopefully have something out soon on that. We're also planning to look at generating a very large label data set from these Wikipedia tables we already have to essentially train semantic modeling systems so they actually perform better. Okay, and then here's my final slide. And this is just a link to both the tools and the papers on this. So here, if you go to karma.isi.edu, there's a link to a GitHub repository, a user guide, and a very nice tutorial that will teach you how to use it. Karma is a supported tool where you have a student that answers questions and addresses any bugs or problems people find. And then we have more recent work that the student, PhD student Ben Vu's been working on, which is a recent paper that just came out, which is a link here. And then there's the link to the GitHub repository where you can download and run this tool. Okay, I think now we can go ahead and take questions, and I think we do it in the event X side. So I'll go over there and see if you guys have any questions that I can answer.